significant figures and precision. Significant figures represent the precision of a measurement. For example, the world record for the 100-meter race is 9.58 seconds. So here you see in this number there are three significant figures which are 9, 5 and 8. Here 9 and 5 are called certain digits and 8 is called uncertain digits. So it means when you say the time is 9.58 seconds, then the last digit is uncertain. It can be 9.57 or it can be 9.59. Okay. Similarly, the world record for the high jump is 244.9 centimeter. So again, here you see that the last digit 9 is again uncertain and rest of the digits are certain. So all certain digits plus first uncertain digit are called significant figures. So in the case of this 9.58 second, there are three significant digits 9, 5 and 8, while in the case of 244.9 there are four significant digits which are our old 244.9. So in this way this represents how precise a measurement is. Okay, so now I will tell you about some rules which are used for counting significant figures in a given numbers. Rule number 1 is that all non-zero digits are significant. For example, if you have a number 238 centimeter, then all digits are non-zero, so it has three significant figures. Second rule is zeros between non-zero digits are significant. So here in this number 2.308 centimeter, you see even though there is one zero, but it is in between non-zero digits, so this is also significant. So this number has four significant digits. Rule number 3 is that if the number is less than 1, the zeros on the right of the decimal point but to the left of the first non-zero digit are not significant. Let us look into this number. Here what you are seeing in this number, that there is a 0 which is to the right of this decimal point but to the left of any non-zero number which is 2. So this 0 in this particular case is not significant. So this overall, this number 0.02308 has only 4 significant digits. Rule number 4 is that trailing zeros without a decimal point are not significant. In this number 123,000 millimeter, you see there are 3 significant figures. The remaining these 3 zeros which are trailing are not considered as significant figures. Then the rule number 5 is that trailing 0 in a number with a decimal point are significant. So if you write a number like 3.500, then here all zeros are also significant. It has 4 significant figures. So if you are writing 3.500, then one would understand that your precision is up to the last digit 3.500. So your last digit is up to that point your measurement is precise. For any reason, suppose you want to put some more zeros after that, that is not allowed. You cannot put any more zeros after that, because when you write these numbers in certain way, that represents how accurate, how precise your measurement is. So it is very important to be very careful about finding out significant figures. So now the examples of numbers we discussed here in this previous slide were in standard decimal notation. But in this notation, the significance of trailing zeros can sometimes be ambiguous. Let us look into the example. For example, suppose you found a length as 4.700 meters. You did some measurement and you found that object is 4.700 meters. So in this number, there are 4 significant figures, 4, 7, 0 and 0. Now suppose we change the units. We change these meters to millimeter. So we can write 4.700 meter same as 4700 millimeter. The number 4700 millimeter may appear to have just 2 significant figures based on the rules which we learned in the last slide. Right? We saw that trailing zeros are not significant. But that would not be correct in this case, because when you convert the unit, the significant figures should not change. But here, because of this ambiguity, it is changing. To remove this ambiguity, often scientific notation is used. Instead of this simple decimal notation, it is custom to use a scientific notation for most of the scientific work. So in scientific notation, every number is expressed as a into 10 to power b, where a is the number between 1 and 10, while b is a positive or negative number, that power 10 to the power b is any positive or negative number. This formatting removes the confusion about trailing zero. For example, 4.700 meters, if I want to convert it to centimeter, I will just write 4.700 and 10 to power 2 centimeter. Similarly, if I have to write it in millimeters, I will just keep 4.700 and 10 to power 3 millimeter. And similarly, you can do in kilometers, 10 to power minus 3. So you see the number of significant figures remains the same. The power of 10 here is irrelevant to determining the significant figures. What matters is the base number a, which is all the time is having same number of significant figures. So that is why this scientific notation is very widely used. It helps in avoiding ambiguity when we present our results. Another quantity I would like to introduce at this point is the order of magnitude. In some cases, we need to just compare how two quantities relate in a rough sense. We don't want exact numbers, just rough, that how they compare. What matters in such situation is not the exact value, but the order of magnitude, that how they compare. And for doing such estimation, we assume that if a is less than or equal to 5, we round it a to 1, and if a is between 5 and 10, we round a to 10. So in this way, the quantity is then approximated as 10 to power b, and the exponent is called the order of magnitude. Let us look into the example. The diameter of the earth is 1.28 into 10 to power 7 meters. If you round it, it will be 1 into 10 to power 7. So this 7 will be the order of magnitude. Now another example is a tennis ball. A tennis ball has a diameter of 6.7 into 10 to power minus 2 meter. If you round 6.7 to 10, then this diameter will come out to be 10 to power minus 1 meter, and so the order of magnitude will be minus 1. So this is a very useful thing when you have to make some rough